coastline, the undulating mountains or steep summits are not the result of chance, but the result of a huge battle between the forces of the interior of the Earth and erosion, that over thousands of millions of years have been shaping the relief that we can now see.
This is the spectacular structure of the growth syncline of Serra de Busa. We can see here the lower beds, which are vertical to overturn in the lower part, and then the upper beds that show this very smooth syncline on the top. This reflects the synchronous tectonics and sedimentation during 3 to 4 million years during the evolution of the Pyrenees, in which each bed has been folded before the deposition of the next bed to have finally a growth syncline. This structure, which is a very nice structure and very well worked, has been visited by hundreds of different people from everywhere in the world.
This is not a local deformation, but one that embraces the whole Ebro basin.
60 million years ago, the northeast of the Iberian Peninsula was a relatively flat area where the European plate and the Iberian plate started to collide. As a result of this collision, the numerical modeling results show us that the growth of the Pyrenees, the Iberian Range and the Catalan Coastal Range start, and in the center there is this huge lake system trapped, which starts accumulating all the sediment eroded from the surrounding mountain ranges. When the waters found their way out of this lake system towards the Mediterranean, as the numerical model will show, a new river, the Ebro River, formed and started eroding all that sedimentary fill accumulated in the Ebro Basin and transporting it towards what today we know as the Ebro Delta.
Thanks to satellites, we can see, study and analyze the planet's surface by remote sensing.
The main advantage of remote sensing is that we can observe at scales and with perspectives that are appropriate to appreciate large terrain units. A second very important advantage of remote sensing is that we can use instruments that sense beyond our visible range. This is important because many materials have specific responses in this part of the electromagnetic spectrum that is invisible to us. A good example is this region of Puna in the Andes that appears gray and brown at our eyes, that becomes unexpectedly colorful when it is observed with shortwave infrared.
Mountains, plains and coast, constantly changing, thanks to the action of powerful forces.
The landscape that we have here behind me is in constant change and is the result of the action of tectonic processes and erosion. The erosion we can measure in the scale of millimeters and centimeters per thousands of years. All these processes are happening at the scales of time that are much larger than the human time scale. So, in fact, this landscape that we see static, it is not. It's constantly changing.
Rain, wind, ice, floods and flash floods, and the onslaught of the waves continually erode the surface of the Earth. The eroded materials are transported, deposited, and compacted together with organic elements transported by the wind or water. These sediments have been stratified at the bottom of large depressions, of the sea and oceans, and also in lakes such as Banyoles in the province of Girona.
We came here using a floating platform and we extract these sediments and we study them layer by layer. And for example, for the last 2000 years we have seen that the Roman period was a little bit warmer and drier than nowadays, whereas the Little Ice Age, that is a period between the 14th and the 18th century, is a period a little bit colder and rainier than today.
A volcanic eruption produces deposits very quickly. If we can determine the age of these materials, we know the age of the eruption, and we have a temporal marker, very precise in terms of geological time. This information allows us to know that the deposits over the layer are younger than the layer, and the deposits under the layer are older than this.
In the interior of the province of Almera, the river Aigües has cut through layers of gypsum strata about 100 meters thick. These gypsum layers were formed on top of older sediments, which provide us with evidence of cyclical climatic changes. We find them here in Almera, as well as in other places around the Mediterranean basin, such as Sicily and Crete.
There are sedimentary cycles formed in humid or arid conditions. If you see 1, 2, 3, 4, and 5, another 1, 2, 3, 4, and 5. We know that the little ones have a duration of 20,000 years and are produced because the precision. The big one have a periodicity of 100,000 years and are because the eccentricity.
Besides our interest in the correlation of strata in different parts of the Mediterranean basin, the materials deposited themselves provide direct information about the environment in which they were formed millions of years ago.
The conglomerates of the Montserrat Mountains started to be deposited at around 40 million years. The framework of the mountain consists of an interdigitation of conglomerates and fine-grained levels. This interdigitation alternation illustrated about noticeable sea level changes. On the other hand, some of these changes may be related to important global environmental changes.
With all this information, not only do we have an idea of how the climate has changed over the last thousands of years, but we can extrapolate back further, over millions of years. And this gives us a much broader picture of the changes that have taken place on our planet, and therefore allows us to better understand what might happen in the future. If we want to investigate deeper into the Earth, special techniques are needed. One widely used technique is seismic reflection, that consists of emitting waves from the surface, then interpreting and recording the waves that have reflected from various levels within the interior, providing us with valuable information on the architecture and structure of the subsurface.
Seismic reflection methods allow us to make pictures of the structure of the rocks that are underground. Basically, structures like the one that I have in the background, which shows a vertical structure. If they are underground, we're not able to see it. So therefore, if I had some type of ecography, I can actually map the actual architecture.
This way, we can identify structures where there may be hydrocarbon-bearing reservoirs. Another technique is seismic monitoring.
Seismic monitoring is the observation of the subsurface using seismic networks. For example, like this network that we installed in northern Morocco to study natural seismicity. Using seismic monitoring, we can investigate the existence of active faults, see variations in the earth structure, like the water table, analyze the migration of fluids, like oil and gas or CO2, due to the injection or extraction. And we can also study the existence of induced seismicity due to reservoirs, underground gas storages, etc.
The most common surveys are those related to energy resource exploration, be it oil, gas, geothermal or water. But some are carried out for scientific purposes.
We are right now in Lorca, and right now on top of the Alhama de Murcia fault, it is a strike-slip fault that gave rise to the destructive earthquake in Lorca in 2011. Right here, we have been drilling a scientific borehole to investigate the properties of the fault. We have used different geophysical logging tools and specifically an acoustic televiewer that gives an oriented image that we will be using to analyze the deformation in the rocks surrounding the borehole.
In our journey to know the Earth at greater depth, we have to apply other methods, as we cannot drill much below the first 100 kilometers. One such method is to study wave propagation through the subsoil.
A heatquake is a sudden movement in the interior of the Earth in which a lot of energy is generated, which then travels through the Earth in form of seismic wave. If you are able to record this wave in form of seismograms, we can then derive important information about the Earth interior, as for example the seismic velocity, but also the density and other derived parameters.
One way to understand what happens to rocks at depths of 50 or 100 kilometers is to study minerals that are subjected to pressures and temperatures that simulate conditions within the mantle. This is being investigated at the Institute of Earth Sciences, Jaume, Almera.
In the lab, we can study the basic properties of minerals under the extreme conditions of pressure and temperature equivalent to depths of hundreds of kilometers. We can do this by using an instrument like this, a diamond anvil cell, where we have to put a very tiny sample between the anvils of two diamonds. When we squeeze the two diamonds, we achieve high pressures of the order of 20-30 gigapascals.
All this information is utilized to make numeric simulations.
And then we put all together in a mathematical model, in a numerical model, and then we can calculate the actual densities and the actual velocities in the Earth's interior. Once we know the densities, we can calculate how the Earth's interior is moving and how this movement drags the lithosphere. And then we can also predict where we will have extension or compression and what will be the tectonic movement.
Convection within the mantle causes displacement of the Earth's crust, giving rise to continents.
And in some places there are colliding, forming the big mountains like will be the Himalaya and the Tibetan Plateau, that this collision is about 5 centimeters per year. In other places there is a plate that is going beneath the upper plate, where this upper plate is getting deformed and forming some mountain like in the Andes. These movements usually is a bit faster, like 8 centimeters per year. And in other places the plates are moving away and is hot material is going up and forming this new crust.
Highly viscous mantle fluid arrives at the surface at some points on the planet and forms volcanoes. This material, called magma, gives rise to the formation of new Earth's crust.
Changes in pressure, temperature and composition in the Earth mantle may lead magma to start ascending toward the surface in the shape of diapirs. These diapirs are similar to the bubbles that we are seeing here, and because the lesser density, they are able to ascend towards the Earth's surface and finally, at a certain stage, to evolve to volcanic activity.
In the Iberian Peninsula, we have volcanoes. For example, in the province of Girona.
This area is an area that has been active for at least the last 12 million years. So it's probable that we will have eruptions in the near future, geologically speaking, of course.
There are places on our planet where, for reasons that are not fully understood, large accumulations of magma occur beneath the Earth's crust that give rise to the formation of volcanoes at the surface. These places are called hotspots and are responsible for the existence of many islands, such as Reunion in the Indian Ocean, Hawaii and the Galapagos Islands in the Pacific, and the Canary Islands in the Atlantic.
Well, the last eruption from the Canaries, which is this eruption from El Hierro, it's a very important eruption in the sense that it allows us to obtain a full record and, in terms of information from the monitoring system. In this eruption, we have been able to record the full sequence of processes that started when magma was accumulated at several kilometers below the surface, till this magma arrived at the surface and produced the eruption. So this eruption was very similar to the one I have just behind me, which is the cross-cut eruption, but below sea level.
Our journey towards the center of the Earth is full of adventures and wonders even more spectacular than those Jules Verne wrote about in his novel. An immense paradise beneath our feet that we have only just begun to discover.